I used to. 3, 2, 1. Well, I missed it. All right. It's Tuesday. It's the 19th, and we're doing L'Hopital's rule. Kindly consider the following limit. Okay, not that. That. Okay.
Who stole my bag?
Find the limit as x approaches 1 of x to the 4th minus 1 over x minus 1. How do you do this limit? You already know how to do this limit one way. I'm going to show you how to do it another way in case you need this new technique. But do you have any idea how you know how to do this already? Not L'Hopital's rule, that's new. Dun 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 dun. Well, if you plug it in, what happens?
Oh, I know. Okay, you're going to
Do what?
x squared minus 1, x squared.
Factor it out, good.
Then we have x squared minus 1, you're going to make that into x minus 1, x plus 1.
There you go.
Get rid of the
It's so complicated. Good. All right, yeah, you can do this by factoring. Look, the limit. The problem is you can't plug in 1. If you plug in 1, you get 0 over 0. That's bad. You're going to find that in the limit that's not necessarily undefined, 0 over 0. 5 over 0, bad. 0 over 0, indeterminate. Not necessarily undefined, but all right, let's see what we get. So factor by difference of two squares, right? And you can factor again, can't you?
I'm so smart.
It's smarticles. So this is something that can be done by factoring, or maybe even long division if it's not easily factorable. But what's nice about this? It cancels the x minus 1. So instead of having a vertical asymptote at x equals 1, you have a hole. Remember we talked about this stuff? We've seen this before. But now is it a plug-in limit? Can you plug in the 1 for x? Sure you can, because it's 1, that's okay. Now plug in 1, that's 2. Plug in 1, that's 2. You get 4. All right, but what if you couldn't factor it? Here's another way to do it. This is called L'Hopital's method, or L'Hopital's rule. Yeah, if you graph this, it's going to be a hole. When x equals 1, there's going to be a hole in the graph. At x equals 1, yeah. It'll look otherwise like some kind of a cubic if you FOIL this out. Okay? All right, but say you can't factor it, or there's no other way to do it. Here's a new way to do it. Do the same problem again. See if we get the same answer. Now, this is what L'Hopital did. L'Hopital was a famous mathematician. He was the first one to write the first ever calculus textbook. And this rule was in it. Yeah, I said in it. Okay. Although that wasn't standard calculus at the time, he just threw it in there. He says, okay, if when you plug in the 1, you get 0 over 0 case, or for that matter, infinity over infinity. Take the derivative of the top, separate from the bottom. I'm not talking about quotient rule, not low d high minus high d low over low low, right? Just derivative of the top, separate from the bottom. What's the derivative of the top? 4x cubed, right? What's the derivative of the bottom? 1. Now plug it in. If it's still 0 over 0, do derivatives again. If it's still 0 over 0, do derivatives again. As soon as it changes, you either have an answer or it's something over 0, it's undefined. Well, plug in 1. What do you get? Isn't that what we got before? That's exactly what we got before, right? Now, where did he come up with this? He came up with this by graphing tangent lines. Look at this. Take a look at what Hal has to say about this. What if I graph the numerator, separate from the denominator, and zoom in where x equals 1? All right, so here's the numerator, x to the 4th minus 1. And here's the denominator, x minus 1. And how about just zoom 4 for now? And there's x to the 4th minus 1. It's almost parabolic. And here's x minus 1, mx plus b form. It's a line already. But look what happens. If you zoom in when x is 1, let's go to x equals 1 on both curves, right? And now you zoom in there. Enter. Now the parabola looks a little less curvy here. Now this is already a line, but this is starting to look like its own tangent line. That's called local linearization. If you blow up a continuous curve at a point of continuity enough times, eventually it's going to look like its tangent line. Zoom in again. Whoops, F2, 2. Still at 1, 0. And this is the parabola, or the thing that was sort of like a parabola. And here's the line. And what L'Hopital figured out was whenever you have a 0 over 0 or infinity over infinity case, the answer is always the slope of this tangent line divided by the slope of that tangent line. That's why we did the derivative of the top, the slope of the tangent line for the top, derivative of the bottom, the slope of the tangent line for the bottom. If you zoom in enough, you're going to find the slope of this thing is 4, the slope of this thing is 1. All right, zoom in one more time just to make it look even more linear. And this looks basically like a straight line, doesn't it? And this was always a straight line. So if you calculate that slope, you get 4. You calculate that slope, you get 1. 4 over 1 is the answer. That's what L'Hopital observed and proved in his calculus textbook. So let's use this technique to figure out weird limits that we're going to need to be able to figure out because they're going to come fast and furious real soon. Here we go. What about this one? The limit. So the same idea. Limit as x goes to 0 of cosine x minus 1 over x. Well, is that a L'Hopital case? Remember L'Hopital? In the limit is 0 over 0 or infinity over infinity. That's not necessarily undefined. We call that indeterminate because you may get an answer doing it a different way. What happens when you plug in 0? Cosine of 0, 1 minus 1, 0 over 0, right? Okay, let's do L'Hopital. The limit as x goes to 0 of, what's the derivative of the top? Negative sine of x, derivative of the bottom. Now it's not over 0, right? So it's got to have changed from 0 over 0 case to something else. If it's over 0, that's going to be undefined. But if it's over non-zero, that's going to be an answer. What do you get when you plug in 0 now? You get 0. Sine of 0 is 0. Well, you wouldn't need to do it otherwise. If it wasn't 0 over 0, you wouldn't need to do it. You'd have an answer already, right? Okay, so there you go. I don't know if you recall, but we came up with this limit a long time ago using sandwich theorem and convergence tables to figure out the derivative of sine and cosine. This came up, and we found it was 0. So that makes sense. But this is an analytic exact answer. How about this one? Is that a 0 over 0 case? What do you think? If you plug in 0, do you get 0 over 0? Yeah, so derivative of the top is cosine, derivative of the bottom is. So plug in 0, and what do you got? Cosine of 0 is 1. And this is another sandwich theorem problem we got 1 from. Way back when? Well, if you graph this, well, I don't know if I can do justice to this. If you graph sine x over x, it's doing sine wave stuff, but then it does weird things near 0. It's got an open circle there. Okay, stuff like that. And the question is, what is the limit from the right? What's the limit from the left? Well, we sandwiched this between y equals 1 and y equals 1 minus x squared. At least that was one of the ways we did it. And we know that 1 minus x squared is continuous everywhere, and its limit is 1, because it's a plug-in limit. What's the limit as x approaches 0? Plug in 0, it's 1. This is always 1, the limit is 1. So from the right, this approaches 1. From the left, this approaches 1. But this curve is stuck in between. It's sandwiched inside. This one goes to 1, this one goes to 1, but this is stuck in between. So as you get closer and closer to x equals 0, this limit's got to be forced into 1. That's the sandwich theorem. Okay? We also did this with convergence tables and all kinds of stuff. So we've seen these limits before. All right, here's some new ones. What's the limit as x approaches 0 of 3x minus sine x over x? Slightly more complicated. Is that a 0 over 0 case or infinity over infinity case? Yeah, it's 0 over 0, isn't it? 3 times 0, sine of 0 is 0, 0 minus 0 is 0 over 0. Okay, good. So derivative of the top is? Yeah. And derivative of the bottom? 1. So plug in 0, what do you get? 2, right? That's it, done. Okay. limit as x approaches 0, try another one, of rad 1 plus x minus 1, not in the radical, over x. Is that 0 over 0? It is. If you plug in 0 here, you get the square root of 1 is 1 minus 1 is 0 over 0. Fine. So the limit as x approaches 0 of what? How do you take the derivative of this? This is u to the 1/2, right? So what do you get? 1/2 u to the negative 1/2 times du, but du would be 1, right? What's the derivative of this part? 0. What's the derivative of this? 1. So I guess I don't need all this stuff here. And so what does that equal? Is that still 0 over 0 case, or do you have an answer? You sure do. Plug in 0 for x and you get? No negatives. 1/2, that's it. Plug in 0. You get 0 plus 1 is 1. 1 to anything, it's in the denominator really. The square root of 1 in the denominator is 1. Times 1/2 is 1/2. That's it, done. Okay, was that painful? That wasn't too bad, was it? All right, wait, there's more. This is slightly different. The limit as x approaches 0 of x minus sine x over x cubed. Is that a 0 over 0? Sure is. So what's the derivative of the top? 1 minus cosine over what? 3x squared. Perfect. Now if you plug in 0, what happens? It's still 0 over 0. Cosine of 0 is 1. 1 minus 1 is 0. 0 squared is 0 times 3 is 0. You got 0 over 0. Ah! Do it again. Until it changes from 0 over 0. When it changes, it might be undefined, some 5 over 0 maybe, or you'll get an answer. So what's the derivative of this top? Sine of x, because the derivative of the cosine is negative sine, and the derivative of the 1 is 0. What's the derivative of the bottom? 6x. All right, now what happens when you plug in 0? It's still 0 over 0? Yeah, it is, isn't it? Sine of 0 is 0. 6 times. Oh my God, do it again. If it's still 0 over 0, just keep on doing the derivatives. Derivative of the top? Cosine. Derivative of the bottom? Okay, now plug in 0. 1, 6. Good. That's it. So keep on doing it until it changes from 0 over 0. Once it changes, it's either to an undefined answer or to its actual number. You're done. Okay? Here's another one like that. Ready? Can I try another one? Alrighty. The limit as x approaches 0 of rad 1 plus x minus 1 minus x over 2 over x squared. All right, what form is this? Is this 0 over 0, infinity over infinity, or something else? It is 0 over 0, right? Because plug in 0 here, you get 1 plus 0 is 1, rad 1 is 1, 1 minus 1 is 0, and 0 over 2 is 0, so 0 minus 0 is 0, over 0 squared is 0, yep. So, differentiate the top, separate from the bottom, what do you get? 1/2 quantity to the negative 1/2, right? What's the derivative of this piece? 0. What's the derivative of that piece? Negative 1/2, right. What's the derivative of this? 2x equals. All right, well, let's see. What happens if we plug in 0 now? It's over 0, right? So if it's not 0 over 0, it's undefined. If it is 0 over 0, we're going to differentiate again, right? Or plug in 0. Let's see. 1 plus 0 is 1 to the negative 1/2 is 1 times 1/2 is 1/2 minus 1/2 is 0 over 0. Do it again. Don't need all these equal signs. All right, so do the derivative of the top, separate from the bottom again. So what do you get when you differentiate this? Negative 1/4, 1 plus x to the negative 3/2, good. Derivative of this? 0, derivative of that? 2. Well, now it's not over 0, so you've got to get an answer. Plug in x equals 0, what do you get? No, you were right the first time. Negative 1/8 actually, because it's 1/4 divided by 2 or times a half, right? Multiply with the reciprocal. If you plug in 0, you get 1. 1 to anything is 1. It's in the denominator, big deal. Negative 1/4 over 2 is negative 1/8. Done. Okay, how about this one? Are you ready? Now this is different. This is not 0 over 0, but you can still do it. So this is different. What's the limit as x approaches pi over 2 of tan x over 1 plus tan x? Now if you plug in pi over 2, what do you get? Yeah, what's the tangent of 90 degrees? It's 1 over 0. Isn't that where you get a vertical asymptote for the tangent curve? At pi, x equals pi over 2 and 3 pi over 2 and 5 pi over 2. There's all these vertical asymptotes for tangent. So it's undefined there. In fact, as x approaches pi over 2 from the left, it goes to positive infinity. And so does this, plus 1. What's infinity plus 1? It's infinity. So this is infinity over infinity case. Guess what? L'Hopital works here too. Take the derivative of the top. What do you get? 0. Nope. Derivative of tangent of x. Secant squared. Right, exactly. Secant squared x. What's the derivative of the bottom?
1.
Well, the derivative of the 1 is 0, so it drops out. And derivative of the tangent is secant squared again. What's secant squared divided by itself? It's 1. No matter what x is doing, I don't care. Ta-da! Dunsky. Any questions how we did that? Alrighty. So infinity over infinity works just like 0 over 0 case. Okay, this is completely different. Are you ready? Okay, I'm going to make this black. Make it totally different. What's the limit as x goes to infinity of x times sine of 1 over x? Now, what would you classify this indeterminate form? It is an indeterminate form, but it's not 0 over 0, and it's not infinity over infinity in the limit. What is it? Well, as x gets ginormous, right? What's 1 over x doing? Going in, how small? Basically indistinguishable from 0. What's the sine of 0? No, that's cosine of 0. Sine of 0 is 0. So you have infinity times 0. Now, infinity times 0, what the hell is that? Now, see, notice what's going on here. Anything divided by itself, you would expect it to be 1, right? No. This was 0 over 0. It's not 1. This was 0 over 0. It's not 1. This was 0 over 0. This was 0 over 0, right? It's indeterminate. It's not necessarily 1. This one's a fluke. Okay? So 0 times infinity is not necessarily 0. Isn't 0 times anything 0? No, it's not necessarily 0. The idea is to convert this so it looks like L'Hopital. Remember what L'Hopital looks like? 0 over 0 or infinity over infinity. Is there a way to rewrite this so it's a fraction?
Over x.
Not over x, though. You're close. Right idea. Not over x. If you just write this over x, it's different. What would make it the same? Over what? Over 1 over x, right. Look, this is the limit as x approaches infinity of sine 1 over x in the numerator over 1 over x in the denominator. Because how do you divide by this? You multiply by x. It's the same thing, right? But now what happens? As x gets ginormous, 1 over x goes to 0, sine of 0 is 0, and 1 over x goes to 0. So this is 0 over 0 now. That's the trick. So if it's not 0 over 0 or infinity over infinity, make it so, and then apply L'Hopital's rule. Okay, so do it. What's the derivative of the top? Whoops, what did I do? Yeah, what's the derivative of the cosine of u? Sine of u, it's cosine u du dx. Chain rule. What's the derivative of the inside? The inside is u is x to the negative 1. So du dx, the chain rule is negative x to the negative 2, otherwise known as negative 1 over x squared. Over, well wait, derivative of this. Didn't we just do it? So what is it? Negative 1 over x squared. But what's nice about that? They're gone. So ignore them. They're 1. And so now plug in infinity. You can't really do that. But as x gets humongous, 1 over x becomes 0. Cosine of 0 is 1. So 0 times infinity was not 0. There you go. Believe it or don't. This is only true in the limit. These are not functional values. I can't plug in infinity, right? Yeah. Oh, but you're going to need this real soon. Hang on. Wait, this is BC stuff. We're going to need these kinds of limits.
Why does math contradict itself?
Why does who?
Math contradicts itself.
How is it contradictory?
All the time.
Now remember, if you plug in something into a function like f of x, right, and you get 5 over 0, that's undefined. That's not what I'm saying. I'm saying if in the limit you get 0 over 0, that's not necessarily undefined. Yeah, but this is a limit. This is not a functional value. You're confusing the two.
You're like, oh, it can only be the big number subtracted.
But you understand, before now, before limits, those rules were all about functions. Values you get by plugging in x into f of x, say. Whether they called it that or not, those are all functional values. If you get 5 over 0, that is definitely undefined. You're done. If you get 0 over 5, that's 0. That's fine. This is different. This is a limit, and this is 0 over 0. That's indeterminate. It's not defined. It's not undefined. We don't know yet. Right? That's what we're doing. Okay. Try this one on for size. This is not 0 over 0 or infinity over infinity, but you could make it so again. The limit as x approaches 1 of the quantity 1 over ln x minus 1 over x minus 1. Now what if you plug in 1? Yeah, ln of 1 is what? 0. And 1 minus 1 is what? 0. So this is like 1 over 0 minus 1 over 0. Isn't that basically infinity minus infinity in the limit? As x gets closer and closer to 1, this gets closer and closer to 1 over 0. These are numbers are getting bigger and bigger and bigger because you're dividing by smaller and smaller and smaller. So any idea how we could do L'Hopital here? I wouldn't divide. Look at it. It's staring you in the face. It's telling you what to do. Don't you know how to subtract fractions? You need common denominators. What would it be? What do you multiply top and bottom by here? X minus 1. Top and bottom by here. There you go. So x minus 1 minus ln x over the common denominator ln x times x minus 1. I can't write. All right, so there's your fraction as a common denominator. Now what do you have if you plug in 0? That's right, plug in 1. Well, 1 minus 1 is 0. ln of 1 is 0. 0 minus 0 is 0. Okay. ln of 1 is 0. 1 minus 1 is 0. 0 times 0 is 0. This is 0 over 0 case now. Aha! We can do L'Hopital. So, derivative of the top separate from the bottom. Derivative of this is 1. Derivative of that, 1 over x. Good. Now the bottom is going to be a product rule, I guess. So, derivative, so first times derivative of the second, plus the second, times the derivative of the first. Okay. Now what if you plug in 1, what happens? 1 over 1? 1 minus 1. 0 over, is it 0? Yeah, 1 minus 1 is 0 times anything is 0. ln of 1 is 0 times anything is 0. 0 plus 0 is 0. Yeah, this is still 0 over 0. It didn't change. So what do? Do it again. L'Hopital's rule. So derivative of the top now is, well, remember we differentiated this before and it was negative 1 over x squared, but now there's another negative. So positive 1 over x squared. Okay. What's the derivative of ln? This is just 1 times ln, right? So it's just ln. Derivative of ln x? 1 over x. And I guess this is another product rule. Okay. First times the derivative of the second plus the second times the derivative of the first. All right, now if you plug in 1, is it still 0 over 0? Or do you have an answer? Or do you have an undefined limit? Where? Add them up? Well, you'd have to distribute this first. This is not, oh, these two. Yeah, you could.
Would that make it easier?
Maybe. You could do it that way. I don't think it really matters because what if you plug in 1? You get in the numerator? 1. And this is 1 and this is 1. What's this? 0. So what do you got? 1/2. You can combine them or not, but just look at the 2. Okay, now this is one of the most famous limits ever, and it comes up somewhere in part 1 all the time on the AP. So you got to know this limit. Let's see if you can recognize it. This is a weird one. This is the one we did in extra help that day. Yeah, remember that one? This comes up a lot. This is a weird one, so I'm going to make it red. Okay, here we go. What's the limit as x approaches infinity of the quantity 1 plus 1 over x to the x? Well, as x gets ginormous, 1 over x becomes, in the limit, 0. So 0 plus 1, that's the base. And this goes to infinity. So 1 to infinity. Aha, this is weird. 1 to infinity you would imagine is 1, right? Because 1 to anything is 1? Not necessarily. This is indeterminate. Let's see why. The problem is this exponent here. Don't we have a way of simplifying exponential functions?
Logs.
Logs, right. So look, what if I rename this thing y?
Y.
You'll see. Okay, let's rename the thing I'm taking the limit of as y. What's ln y? That'll actually simplify things. X ln of stuff, right? Okay. What if we find this limit? If we figure out that ln of y, say for argument's sake, I'm making stuff up, I don't know. Let's say the limit as x goes to infinity of ln y is, I don't know, 2. Doesn't that tell you what y is? How do you get rid of ln? E to the, and then y's limit is e squared. Now I just made that up. I don't know this. I just made that up. But that's the game plan. I want to know what the limit of ln y is. All right, you'll see. So I'm rephrasing the question. I'm going to say, all right, what's the limit as x goes to infinity of ln y? In other words, the limit as x goes to infinity of x ln quantity 1 plus 1 over x. Okay. Well, what format is this now? As x goes to infinity, 1 over x goes to 0. 1 plus 0 is 1. Ln of 1 is 0 times infinity. This is infinity times 0 again. But we've seen that. Divide by 1 over x. Good. So this is the limit as x approaches infinity of the ln of 1 plus 1 over x over 1 over x. All right, now what do we got? As x gets huge, 1 over x becomes 0. 1 plus 0 is 1. Ln of 1 is 0. And 1 over x also goes to 0. This is now L'Hopital's form. 0 over 0 or infinity of infinity works as L'Hopital. So differentiate the top. Remember, how do you differentiate ln of u? 1 over u times du dx. Right? If that's u, the derivative of 1 is 0, derivative of 1 over x we've seen already. All over the derivative of the bottom. But guess what? We know this derivative. Came up a couple of times already today. What happens? They cancel. So now what? It's not 0 over 0 anymore. What is it? It's this over 1. All right, plug it in. As x gets huge, 1 over x is 0. 1 plus 0 is 1. 1 over 1 is 1. Okay, now remember, that's the limit of ln y. We're saying ln y approaches 1 as x approaches infinity. So what does y approach as x approaches infinity? How to get rid of ln? Raise both sides as powers of e, and you get y equals e. That's it. And that's the definition of e. This is where e originally came from. Euler found this when he was doing compounded interest problems. You take your balance plus your interest rate divided by the number of compoundings times your balance times the do it that many times, that many compoundings. This is compounded interest, x compounded time. If x goes to infinity, x infinitely many compoundings per year, you get interest based on e. You need to know this definition of e. All right, so don't forget your homework assignment tonight. Don't forget your homework assignment tonight. You have that new homework sheet. All those L'Hopital questions. Enjoy.